All right. So we're in chapter 14, acids and bases, and we had to end this chapter before we got a chance to finish it last session. So I'm going to pick up and call this part 2 for chapter 14, acids and bases. I'm going to back up just a few slides so we can sort of dovetail the last one into this lecture. You'll recall that when we have an acid, and this is our generic acid, and it reacts with water, it's in equilibrium with the conjugate base of this acid and the hydronium ion, which is the consequence of transferring one proton from this one proton from this acid to water. Now that the water serving as a base delivers a conjugate acid. And we can write the expression for that, equilibrium expression, which will give a small a as a subscript. And that's our equilibrium expression for the weak acid. And notice we do leave water out of this because water is a pure liquid, so it doesn't count. But then we move to the topic of percent dissociation. And that just means how much of the original acid was dissociated to produce its conjugate base and the hydronium ion. So percent dissociation would just be the concentration of A divided by the equilibrium concentration of the undissociated acid times 100. Then we move to the concept of how does this calculation compare with the equilibrium constant? And it's really analogous to the chapter 13's discussion of equilibrium versus the equilibrium constant versus an equilibrium position. The equilibrium constant is a constant. As long as you don't change the temperature, it will be constant. And these values at equilibrium will change in order to maintain this constant value. Whereas the equilibrium position is more akin to an absolute concentration shift. So if our system is at equilibrium and we disturb it, then Le Chatelier says it's going to move in such a way as to alleviate or ameliorate that disturbance. And the concentrations that are required to reestablish equilibrium will not be the same as the concentrations before you disturbed it. Now that concept, we can translate that into acid dissociation. And similarly, the constant for acid dissociation is a constant at a given temperature, and it will always be constant. And these values will shift in order to maintain that value at constant. But if we do change the concentration of, say, the undissociated acid, say we increase it, we increase the concentration, what happens to the percent dissociation? Well, the percent dissociation, being analogous to the equilibrium position, will change. And characteristic of acids, weak acids, when they dissociate, if you increase the concentration of the undissociated acid, the percent dissociation goes down. So, now to this slide. And this is really a test of your conceptual understanding. The value of Ka for a 4 molar formic acid solution would be compared to the value of Ka for 8 molar formic acid solution. Would they be higher than? This one be higher than? That one would be higher or the same or lower than the 8 molar formic acid solution. And of course the answer is they're the same, because the constant doesn't change as long as the temperature is held constant. So this concentration has no bearing on the K value for the reaction. Now, if we're looking at percent ionization, and I used the wrong terminology, my apologies, percent dissociation actually might even be a better term, but let's be consistent. The percent ionization of the HA will be different. This is an expression of the equilibrium position, and the percent ionization will change with concentration. And if we follow the concept that was explained in part 1 and reiterated just a few minutes ago, the percent ionization for the lower concentration of acid is higher than the percent ionization for the high concentration. So the lower the concentration, the higher the percent ionization. So then we moved, during part 1, we moved to a discussion of why that is and justifying it mathematically. So if we simplify this equation in such a way that we remove the water, and the dissociation constant is going to be the same whether we call this a proton or a hydronium ion. It's still going to give you the same value. Then our expression becomes this. And if we try to solve the equilibrium concentration based upon the starting position, so we give it we establish a certain concentration of HA at the beginning, and then it will shift, partially deionize. And what's happening is, in order for this one to produce the equilibrium position for HA, some of it has to be lost. But since it's a weak acid, that amount that's being lost is very small. So we can ignore this X value, and then we can say the equilibrium concentration of HA is very close to its starting position, or starting concentration. The initial concentration is what the little 0 means. Then the concentration of protons will be equal to the concentration of the conjugate base of the acid, which is equal to X. Then if we write the expression, and all this can be traced back to the ice table. We haven't drawn the ice table up here, but if you draw out the ice table for this equilibrium, then you'll find that these values are valid for that expression. And the concentration of protons times the concentration of conjugate base, which is the same magnitude, divided by this value at the beginning, our starting position, will be equal to Ka, or at the very least, within 5%. Now we're going to change the concentration of HA to begin with, such that the new value is 1/10 of its original value. So we're decreasing the concentration of the acid, the HA, undissociated. When we do that, then we find that the new concentration of the conjugate base and the proton will be 1/10 of its original value. The new concentration of HA then will also be 1/10 because we reduced the concentration by 1/10. We established that value. Now what happens to the equilibrium? Well, we're not sure. We don't know which way it's going to move yet. So we use our equilibrium skills developed in the last chapter and calculate the Q value for this equilibrium. So our new concentrations here and here will be 1/10 of X, and the new starting position for HA is 1/10 of that value. And when we resolve these fractions, we find out that this term here is still equal to Ka. Only now it's multiplied by 1/10. So the Q for our new lower concentration for HA is 1/10 of the Ka. So what happens when the Q is less than K? Which direction does the equilibrium shift? If Q is less than K, the system adjusts to the right to reach a new equilibrium. If it adjusts to the right, that means it has to dissociate or ionize HA even more. So when we decrease the concentration of HA, we cause the shift to the right, which means a higher percentage of dissociation of HA in the process. That's the justification for our rule of thumb, which says if you decrease the concentration of your acid, you increase the percent dissociation or the percent ionization of the acid. So the pH, what would be the pH of a 4 molar formic acid solution compared to the pH of an 8 molar formic acid solution? Now, we just said that the percent ionization would increase for this one. It would be higher. But remember, we're talking about a shift in position, and if you increase the concentration, you're also increasing the concentration of hydrogen or hydronium ions. So even though the percent dissociation is higher for 4 molar, you still have more hydrogen ions in that solution, which means the pH would be lower for the higher concentration. That means, well, the way they're wording it, the pH of this one would be higher than that one, so that means the pH okay, wait a minute. The pH of 4 molar formic acid solution should be, oh, excuse me. The pH will increase, means it becomes more basic than the 8 molar. All right. So the more acid means lower pH. Or basic means higher pH. Okay. So since we have actually increased the number of hydrogen ions for this one versus that one, this is fewer hydrogen ions, which means the pH would be higher, more basic. Everybody get that? I see lots of heads nodding. Good. We'll move on then. Now, this problem asks us to calculate the percent ionization of 4 molar formic acid solution in water. What do we need to do that? Well, first of all, we need the balanced equation for formic acid. So HCHO2 is formic acid, which dissociates into, for simplicity's sake, 1 proton and 1 formate ion. Now we can set up our ice table, and the initial concentration of this undissociated or unionized acid is 4 molar. And of course, at the beginning, we have no acid, no conjugate base. Now, what kind of change are you going to have? Well, we don't need to calculate Q. If these are 0, it has to move that way. So we're going to lose, since it's 1 to 1 to 1, we're going to lose 1x here. We're going to show up over here with 1x and also show up with an x over there. Right? So the equilibrium position then is 4 minus x for the unionized acid. Then we're going to show up with an x there and an x there. What other piece of information do we need? We have to know the K. We have to know the K value for this reaction. And as it turns out, that K is 1.776 times 10 to the minus 4. And that is equal to this value times that value, divided by this value. Okay, so far so good. Since this is a weak acid, and we know so because this is 10 to the minus 4th, it's very weak, which means that this value here, this x, is going to be 4 orders of magnitude less than 4. So we can essentially ignore that value and say we can approximate this value by x squared divided by 4. And then that is equal to 1.776 times 10 to the minus 4. Okay? Now, we need to solve for x. Why? Because if we know what x is, we know how much of this dissociated in absolute terms. So if we solve that for x, we find that 4 times this, I guess I better work that out. Well, it's been worked out. 4 times that. Over here, then to find x, we just take the square root of both sides. That's why x equals the square root of, and we just go ahead and multiply it out. There's no hurry. 1.776 exponent 4, change sign, and then times 4. So we need 7.104 times 10 to the minus 4. And then x equals square root. Where's my square root? Here it is. 2.67 times 10 to the minus 2 molar. So that is the molarity of this ion and that ion. And if we go back to our definition of percent ionization, we have this value divided by that value times 100 equals percent ionization. Right? So we need, let's be meticulous about this. So what we're looking for is, actually you can say either that one or that one, doesn't matter. You get the same answer. Divided by the undissociated, which will now substitute the values. 2.67 times 10 to the minus 2 molar divided by the original molarity, which is 4, times 100 equals what? And I get 0.666%. It's an evil number. There we go. Rounded off to 0.67. So now we have calculated the percent ionization of a 4 molar solution, starting concentration 4 molar formic acid, as long as we know what the K value is. So what would be the pH of this solution? Well, at equilibrium, we now know the concentration of hydrogen ions. So we can calculate the pH. All we have to do is go back to our definition of pH. Let's see, that's percent ionization. I'll leave that there. This is the concentration of hydrogen ions, 2.67 times 10 to the minus 2 molar. So since our definition of pH is the negative log of that value, and we just take the log of that, change the sign, oops, try that again. And we take the log of it and change the sign. And the pH is 1.57. Okay? Since there's no objection, no questions from the audience, we'll move to the next slide. All right. So where do we go from here? Let's take a brief journey back in our lecture series to Arrhenius. Arrhenius said that bases produce hydroxyl ions from the structure of the base. So that means the base would have to be something like this so that we could dissociate a hydroxyl, or that, or even that will produce a hydroxyl. Bronsted and Lowry modified that so that we could account for basic solutions produced by compounds that did not come pre-programmed with a hydroxyl. such as, well, actually, what produced this? Okay? And then this dissociates, of course, into, and there's your hydroxyl. But what Bronsted and Lauer said was, this is a base, not because it produces directly hydroxyls. This is a base because it accepts protons. So if ammonia accepts a proton from water, then that leaves the hydroxyl, and that's where it comes from. Now, if our compound happens to be endowed with a hydroxyl to begin with, those are generally strong bases. So all of the alkali metals produce strong bases, and then one of the alkaline earths, hydroxides, is a strong base. Okay, now if we go back to our definition, suppose we want to know the pH of that solution that forms from the hydroxyl. Yes, we have discussed that relationship. Just checking my notes. Okay. By the same method, Sorensen, we need to find pH as a negative log of the hydrogen ion concentration. We can take that same concept and define the pOH as the negative log of the hydroxyl ion concentration. Carry it one step further. If Ka, well, actually, not just Ka, Kw. Kw equals the hydrogen ion concentration times the hydroxyl ion concentration. Remember, from our equilibrium of water, pure water reacting with itself produces hydrogen ions and hydroxyl ions. And then the equilibrium expression for Kw is just these two because water is not included. But if we take the negative log of both sides, we get the negative log of Kw equals the negative log of hydrogen ions. And then when you take a log of a product, it becomes a summation plus the negative log of hydroxyls. Then we resolve each one of these terms. Negative log of Kw is pKw. Negative log of hydrogen ions is pH. And then the negative log of OH is pOH. So pKw equals pH plus pOH. And since pKw for water is always 14 at 25 degrees centigrade, then we can solve this equation for either one. If we know pH, we can find pOH, just subtract it from 14. If we know pOH, subtract it from 14 and we can find pH. That's all it's saying right there. Okay. So now, we had a discussion in part one of finding the pH of a strong acid solution. Very simple. Strong acids dissociate completely. So if you know the original concentration that you established with your strong acid, you automatically know the hydrogen ion concentration. And that can be used to calculate the pH. But what do you do with a strong base? If a strong base is dissociated, like sodium hydroxide, is dissociated into sodium ions and hydroxyl ions. And of course, these are all in solution. I'm not writing aqueous for every one. Then what's the pH if we start out with 1 times 10 to the minus third molar? Okay. Do we know anything more about this equation? Of course. With a strong base, that's the same concentration as the hydroxyl. So we can calculate pOH, correct? Negative log of 1.0 times 10 to the minus 3. So since we've got a 1 here, this is easy. This is base 10, right? So that means this is minus 3. Log of this term is minus 3. Change the sign is 3. So there's a pOH. Now how do we find pH? Well, pH then is 14 minus 3, which is 11. So the pH of that solution is 11. Okay? Hearing no objections from the audience, we'll proceed to the next one. So calculate the pH of 1 times 10 to the minus third molar calcium hydroxide. All right? The best way to keep yourself out of trouble with these calculations is to have your balanced equation in front of you. If you have a balanced equation that you've written correctly, of course, then you can't go wrong. So what does calcium hydroxide look like? Well, calcium is 2+ ion. Hydroxyl is a -1, so we have 2 of them in that compound. Since it's a strong base, it will completely dissociate. And produce calcium. And how many hydroxyls? For every 1 calcium hydroxide that we put in solution, we get 2 hydroxyls. So what concentration does that make the hydroxyls? Times 2. Right, it's still a strong base, but in the process of dissociation or ionization, it produces 2 hydroxyls for every 1 of the original molecule. So now we have pOH is equal to the negative log, not of 1 times 10 to the minus 3, but 2 times 10 to the minus 3. Okay, so this one I have to use my calculator because I don't have the log of 2 memorized. Okay, so we get this term in here is minus 2.70, rounded off. So that's this part right here. So now change the sign. It's pOH. Then we can calculate pH. That was the question. Yes, pH is equal to 14 minus 2.70, which is 11.3, is it not? Yes, as your pH. Now, why do we bother? Since we already know what pOH is, why do we bother converting it to pH? Because when scientists discuss acids and bases, they always revert to pH as the common tongue. So we got to be able to convert POH to pH. And the only reason that we calculate POH in the first place is because the conversion is so much easier than finding out what the concentration of acid is in this hydroxyl solution. Finding out what the H plus concentration is much more difficult than doing it this way. Okay. All right. So now we move to weak bases. The expression for weak base is in terms of Kb instead of Ka. So for this reaction, what is a Bronsted-Lowry base? A Bronsted-Lowry base is a proton acceptor. So if you think you have a base, but it won't accept a proton, you don't have a base. Fortunately, in this reaction, the cyanide ion will accept a base. It's not a strong acceptor of a base, that's why it's weak. I mean, a strong acceptor of a proton, that's why it's a weak base. Okay, what do we get? From the base, we get a conjugate acid and hydroxyl. Okay? So what's the Kb expression for this one? Well, the Kb is going to be, just like any equilibrium expression, it's going to be this value, the conjugate acid, times the conjugate base of water, divided by the original base. And we don't include water because it's a pure liquid. So that's your Kb expression for cyanide reacting with water. We've seen this one before. I'm not sure why it's there. So we gave a Kb expression for this one. And how do you know whether you're using a Ka or a Kb? Well, one of the reactants, the reactant with water, has to be a proton acceptor to be a base. And if that's true, then you write the Kb expression. So let's look at another one. This one we actually have a Kb value. We also have an error in the slide. This is supposed to be an arrow, actually a double barbed arrow, because we're in equilibrium here. So if we take ammonia, dissolve it in water, and it's going to react and accept a proton from water. So water is now the proton donor, that means it's an acid. Ammonia is the proton acceptor, it's a base, and produces the conjugate acid of ammonia plus the conjugate base of water. And the Kb expression then is equal to the ammonium ion times the conjugate base of water divided by the original base. Okay? Now, this expression, turns out this is very typical of an acid-base type. This is the result of an ice table. So I'm going to do the ice table just to prove it to you, and then you will see it this way very often. Okay? So we have a 2 molar solution of ammonia. Water concentration will not change, so we don't have to include it. Plus, it's not in this expression. Okay. So water, we ignore water in the ice table. And of course, start with 0 there when you put this in solution. Now what's going to happen? Well, the ratio is 1 to 1 to 1. So when 1 shows up over here and 1 shows there, we had to lose 1 from this side. So now we have this, 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 and 2 minus x here, x there, and x there. So now I'm sure you can see it shaping up. The KB, which is 1 times 10 to the minus 5th, 1.8 times 10 to the minus 5th, right, is equal to this one times that one, which is the 2 x's, divided by this concentration. Okay, I think you can see where this is going. Since it's a weak base, x is going to be very small compared to 2 molar. So this now becomes x squared divided by 2.0 is equal to this number. Now we can solve for x. We just multiply 2 times this, take the square root of it. There we go. So now x is 6 times 10 to the minus 3 molar. Now what does that mean? Well, look what x is. X is the hydroxyl concentration, right? So if this is the hydroxyl concentration, and the question is, what's the pH? Then naturally, we're going to take the negative log of this and find the pOH. Six times 10 to the minus 3. Take the log, change the sign. 2.22. That's the pOH. Now the pH is just 14 minus that value. Which will be 11.8. Rounded off. Okay? Any questions? No questions? Let's move on. Let's see what the next slide says. Before I erase that, we might need it again. Oh, we're moving to polyprotic acids. Okay. We finished talking about bases, weak bases. So now we're going to talk about polyprotic acids. And I think in part 1, stream of consciousness led me to describe some things about polyprotic acids. But it never hurts to reinforce. Okay, polyprotic acid is any acid that produces more than 1 proton. So that could be, well, let's do monoprotic acids. How about that? Monoprotic is like that, or like that. And those are strong acids, right? Diprotic is a category, subcategory of polyprotic. Diprotic acid might be sulfuric acid. So it has 2 hydrogens. Oh, I left out, let's get a weak acid over here. C2H3O2 is acetic acid. It's a weak acid, 2 strongs. This one is a diprotic. A triprotic acid would be phosphoric acid, right? But these are classified as polyprotic. Okay, so how do polyprotic acids dissociate? How do they ionize when they go into solution? They ionize in steps, one proton at a time. So let's take phosphoric acid. That'll give us 3 protons to work with, okay? So if we write an expression for the dissociation of phosphoric acid, first proton comes off and leaves us with what? Well, we've got 2 hydrogens left along with the phosphate group. But when one proton left the molecule, it didn't take the charge with it. It didn't take the electrons with it. So that means the electrons are still over here. Okay, so that's the first dissociation. So what's the expression for that dissociation? Well, we have a Ka, and since we're going to dissociate more protons as we proceed, we're going to give that one another substrate. Oh, excuse me, what I'm thinking. This is the first dissociation. Okay, so the expression here is that proton plus the conjugate base divided by H3PO4. That's the expression for the first dissociation of a proton from a polyprotic acid. Now what happens? Well, you still got some of this, and of course, it can go backwards, but while it's in this position, it may decide, instead of going backwards, it may decide to dissociate another proton. That can happen. So what happens then? H2PO4 now becomes, instead of the conjugate base, it becomes the acid for the next ionization step. So we take another proton off of it, and what does that leave us with? Well, we had 1 minus to start with. So now we're going to have 2 minus. And all you have to do to be sure that you've got the right charges is a 2 minus and a 1 plus is 1 minus. So we're still balanced. Now what's the expression for this one? Well, it's the second dissociation. So it's going to be another proton times the conjugate base of this acid divided by that expression. Okay? So, similarly to this scenario, we now have a conjugate base that can act like an acid. So it can either act like a base and go backwards, accepting a proton, or it can act like an acid and dissociate that last proton. So since that's the one we're interested in, we're going to treat it like an acid and let it dissociate its last proton. Okay? Now, the last K value, Ka3, then will be another proton times the last conjugate base divided by HPO4 units. There we go. Now these are the equilibrium expressions for each one of these steps. That's important. Polyprotic acids always dissociate 1 proton at a time. Now, how are these related? It's fairly relative to the others. It's easier to extract 1 proton from this acid than it is from the subsequent acids. And if it helps for you to rationalize that, consider what happens when you extract 1, or when you ionize 1 proton, you get a negative ion here. And if you're trying to remove another positive ion from this negative ion, it's more difficult because of electrostatic attraction. So this value is going to be greater than this value. And consequently, it will be greater than this value. So each step in the dissociation of a polyprotic acid becomes more and more difficult. So these become much smaller still. So which one of these steps is actually the dominant step for creating protons and consequently influencing the pH of the final solution? Typically, this is the only one that matters to the pH of the solution. Now, if we have time, we can prove that. All we need is to know what are the K values. Then you can run through an equilibrium balance ice table, find out what the pH is here, then take the concentration at equilibrium here and use it in another ice table, find out what this one is, and compare the two. I think you'll find out that this one is extremely small compared to that one. And this one is even smaller still. That's how you judge the pH of a polyprotic solution. But that doesn't mean we don't do these steps, because you may want to know, well, what's the final concentration of phosphate in that solution? Because phosphate is a very reactive species in some cases. So we may actually want to know what that is. So we need to run through each step to find out what this one is in solution, and then that will tell us how much of that is available for a reaction with maybe some other metal ion. So here are the K values for each one. The first one is 7.5 times 10 to the minus 3. And the second one is 6.2 times 10 to the minus 8. So a 5 order of magnitude difference there. It's quite a lot, like 100,000 difference. And then this one is 4.8 times 10 to the minus 13, was it? 13. So we have another 5 orders of magnitude. Right. So the K values tell us that we were right in our previous assumption. This is the dominant reaction, and these are less significant. And there we need another double bar here, but for some reason, PowerPoint doesn't like my graphics. Okay, so Ka1, we set up our ice table, and we end up with this familiar expression. If we're starting with a 1 molar solution of phosphoric acid, then we just solve for X, and that gives us, let's see, we're going to check the 5% rule just to be sure. Nope, we're off. So we made that assumption that X wasn't significant, but at 1 molar, X is significant. So we have two choices. We either go back and do the quadratic and find out what X really is, or we do an iterative process. And what that means is we would take this value for hydrogen ion concentration, and we put it back down here, and then resolve for X. It may take a couple of tries to bring you down below 5%. So if we substitute that value into X in the denominator, because that's the one that we estimated before as being insignificant, so we're actually going to put a number in there this time. And when you do that and solve for X, or the hydrogen ion concentrations, and check it with the expression for K and see how does it compare to K, we now are below 1%. So our new value for X, this is the value that's true. And it was less painful than using the quadratic equation. So now we have a value for hydrogen ion concentration right here. And if we convert that to pH, we find that the pH, based on that first dissociation, would be 1.08. So how would the pH change if we took into account the second dissociation? Well, this would be our starting point for the second dissociation in our ice table. Remember, for the first dissociation, we said these are 0. Now for the second dissociation, we're actually starting with that hydrogen ion concentration here, and the new concentration of this is that value. So it would go in here, and this would be 0. Then you run through the whole process again. And are we going to do it? Okay, so the slideshow wants us to go ahead and run through this one all the way down to this one and find out what this concentration is. Okay, we are going to calculate these as intermediate steps. So it's doing what I wanted to, only it's going even further. All right, so now this expression is for the second dissociation, and these are our new starting positions, right? We produced these ions from the first dissociation with none of that. Then we've got this setup, and we're going to solve here. So there's our second dissociation, our second K value here. And there's our expression. There's our expression. We're going to, what are we going to do? We're assuming that X is small, so small that it doesn't matter here. Okay. So how did I end up with that value? 6.2 times 10 to the minus 8. Okay, let me back up. Okay. We got to see, how did we get from, if we say that X is so small that it's insignificant here, then if X drops out here and here because they're comparing to the same number, then these two cancel, and that means X equals X. Right? So if X equals X, then we're going to say that the hydrogen ion concentration is actually equal to the value of K. There's the value of K. Right? Because what did we say before? Come on, go back up. This X is equal to that value. Okay? So now, we're saying that the hydrogen ion concentration actually is, what did we start with? Plus an X, which is this value. So it's essentially the same as it started with, right? We haven't changed it that much because we're still 6 orders of magnitude different, right? So the calculation here tells us that this one and this one have virtually no influence on the hydrogen ion concentration of the solution. And our original pH calculation tells us that's what the pH of the solution is. But the original question was what? What's this concentration? Well, since this is the only place that that one appears, we do have to proceed through these levels and find out what that is. right? It's not like we've already done one of them before. This is all by itself down here at the bottom, and it has to be calculated separately. All right, so we'll go ahead and use this value. So there's our K value, there's our expression right here. And then this is going to be inserted there. And this one now is our new HPO2 minus concentration, which we said was X, right? So that one has to be the concentration for HPO2 minus. And these concentrations are this is the original hydrogen ion concentration, right? We set those equal, solve for this value, and we find that the concentration of PO4 3 minus is vanishingly small. But still, it is a real number and a value that in some circumstances, it would be necessary to know that. And in fact, consider this. What would happen if we introduced ferric iron into that solution? It's going to react with this value here, form an insoluble compound, I believe. Let me check to be sure. I'm pretty sure it's insoluble, but I want to find out for absolute certain. Oh, no solubility charts here. I wonder if there are any previous solubility charts that would help me. I'm almost positive it's insoluble. I'm going to operate on that premise. Iron 3 phosphate is insoluble. If that's the case, then this is removed from solution. And what does that do to the equilibrium position? Shifts it this way. That means this drags more of that into this reaction, which in turn drags more of that into this solution and uses up more of that. So it's sort of a, these are I forget the word. All of these reactions are connected. And it will keep removing PO4 3 minus even at this small concentration, because it will continue to reestablish equilibrium until all of that is used up, or all of this is used up. So if we just have enough to remove some of that, then it'll keep shifting until all the iron is used up, and then it'll reestablish at a different concentration, because now we're starting from a different concentration here. So you would have to go back and recalculate the whole thing. That's where Excel comes in handy, because you can set up all these calculations in Excel, and if you change something at the bottom, everything calculates again. So I hear some of you bad-mouthing Excel. Don't do that. It's an excellent program and help for chemists. Okay. So now let's define what a salt is. In chemical terms, not in culinary terms. A salt in culinary terms, sodium chloride. And potassium chloride is light salt. But a salt in chemical terms is simply what you get when you combine an acid with a base. How does that happen? Well, recall that if we combine, let's use a real example. Say we have hydrochloric acid combined with sodium hydroxide. And the sodium reacts with the chlorine, and the hydrogen ions react with the hydroxyls to produce water. Now, of course, we know this is aqueous solution. So those ions are still in solution. But when you combine an acid with a base, you always get a salt and water. Okay, that's the chemist's definition of a salt. The anion from the acid and the cation from the base combine to produce a salt. Now, we're going to approach this problem qualitatively first. What would you expect the pH to be in general terms, acid, neutral, or basic, if you combine strong and weak acids and bases together in different combinations? So what effect does that have? Well, let's take this one first. Strong acid, strong base. Okay, what do we mean by strong? Well, that acid is going to be completely dissociated. That base completely dissociated. So that means that you're going to have all the chlorine, all the sodium over here, and then all of these protons and all of these hydroxyl ions will be able to combine, right? So what they will do is they will produce water. So what does water do in solution? Well, it just dissociates like it normally would, like that. And it dissociates to the tune of 10 to the minus 7th molar here and 10 to the minus 7th molar there. Right? What does that mean? That means neutral. Because the negative log of 10 to the minus 7th is pH 7, and pH 7 is right smack dab in the middle of your scale. That's neutral. So anytime you have a strong acid and a strong base combined, you get a neutral pH solution. Okay, so let's complicate this story a little more. If we have a solution that forms from a weak acid, let's see. Okay. So if we're going to combine a, let's say, sodium hydroxide, which is a strong base, plus a weak acid, well, the same type of reaction occurs. We get sodium fluoride plus water. But what does that mean for the pH of the solution? All right, rule of thumb first, rule of thumb, and then we'll go into the chemistry. Rule of thumb is a strong acid and a weak base produces a basic solution. It favors the strong base. Okay? That's just a rule of thumb. But why does it do that? Well, you might want to think that it's a basic solution because of this strong base. But actually, it's a basic solution because of this stronger base. Right? What happens to this one when it dissociates? If this is a weak acid, this is an extremely strong conjugate base. Okay? So when it produces these fluoride ions, by driving the reaction over here, then what you're producing there is fluoride ions, and those fluoride ions will react with any water that's there. It could be this one, it could be any other. Those fluoride ions will react with water, and I'm going to subdivide this here. React with water, and remember, if that's coming from a weak acid, this is a very strong base, a very strong proton acceptor. So the reaction here is driven heavily that direction as it takes a proton from water. So in that case, it produces the HF ion, the HF molecule, plus the hydroxyl. Okay, that's why the solution is basic, not because of this, but because of that. Okay, so what's next? Well, that was a strong base and a weak acid. What if we have a strong acid and a weak base? Okay, in that case, we're going to transfer this proton to here. So if this is a weak base, that means this is a strong acid, conjugate acid. If this is a strong acid, then it produces a weak conjugate base. Okay? So now what are we dealing with? Well, once we get to this side, once we get to this side, we have a weak base which doesn't want a proton. It wants to stay just like it is. So it's not going to extract a proton from water. It would not do this and produce that. Right? It won't do that because it's a weak base. But this one will react with water and produce hydronium ions plus ammonia, our weak base. Strong acid will dissociate to produce that weak base. And as a consequence, it will transfer a proton over to this water. That makes your acidic solution. So now I should have done the rule of thumb first, but 6 of 1, half a dozen. A strong acid and a weak base combined will give you an acidic solution. Okay? Now the other way to look at these things is, suppose you take the salt itself and dissolve it in a solution. So the first one we had was sodium fluoride, aqueous. And because this fluoride is a strong base from a weak acid, it's a strong conjugate base, it extracts a proton from water and produces a hydroxyl, which makes a basic solution. But this one, if we had this salt and put it in solution, then the weak conjugate base, that is chloride, will not extract a proton. So it won't produce a hydroxyl. But this one is a strong acid from a weak base, so it will give up its proton. A Bronsted-Lowry acid will give up its proton to a water and produce an acidic solution. Those two situations, actually three, strong acid, strong base, neutral solution, strong base, weak acid, basic solution from the salt that is formed from those two. And the salt formed from a weak base and a strong acid will make an acidic solution. Okay? Now, what's the other scenario? The one that we haven't talked about yet. The one that we haven't discussed yet is the problematic one. What if you combine a weak acid and a weak base? What pH do you get? It depends on the K values for each of the acid-base combination. Okay? This is a table showing what we've done so far. Right? If your cation is, let me see, that should say strong. Neutral, neutral. Okay, so the cation anion here, these are from strong acid, strong base. Gives you a neutral solution. If you have a weak acid and a neutral, you're going to have a basic solution, sodium fluoride. And then our next one was from a conjugate acid of a weak base, and neutral gets you that one. Now when you get to the case where you're a conjugate acid of a weak base versus a conjugate base of a weak acid, then the value of your whether it's acidic or basic depends on the comparison of your K values. And there's an example, aluminum sulfate. So I'm just going to give this to you right now, and we'll try to explain it in a minute. Okay, let's go back. Hold on a second. Let's go back. So if the cation, let's put these up here. Okay. If the cation is the conjugate acid of a weak base, so what would a weak base be for this one? Well, it would be aluminum hydroxide. That is a weak base. So what's the conjugate acid? Well, we're going to produce, this is a polyhydroxyl. So eventually we'll get down to that one. And that makes, since this is a weak base, that's a strong acid. It's a very strong proton acceptor. Right? That's not right. That's not right. We produce that plus this. Okay. Now what this does is it allows this strong base to accept protons. And this one is the conjugate base of a strong acid. Right? So this one can be visualized as the consequence of dissociation of this to produce a sulfate. So when you have the sulfate from here, it's not going to combine with hydrogen ions. Well, it'll combine with one, because the SO42 minus, coming from a weak acid, is a strong base. So it is going to extract a proton from water and produce HSO4 minus plus hydroxyl. So that'll produce a basic solution, and this will produce, this one should produce an acidic solution. So that will produce an acidic, this will produce a basic. And what you have to do is compare which one dominates. Which one of these favors that one strongly or this one strongly by comparison. So that's where the Kas and the Kbs have to be considered. If the Ka for this one is greater than the Kb for that one, that means this one dominates and it's going to produce protons versus all of these hydroxyls. So when the Ka for this, for the cation, right, the Ka for the cation is greater than the Kb for the anion, what's the consequence? pH less than 7. So we can take the converse of that. What if the Kb were dominant? The Kb for the anion is greater than the Ka for the cation. Then the pH would be greater than 7. Right? Because then this one would dominate over that one. And of course, if the Ka equals the Kb for a weak acid, weak base combination, your solution will again be neutral. Okay, so let's take a real world example. That was a real world example. It's just, it might be a little harder to follow. Let's take another example and see if we can make sense of this one. Calculate the Kb values for the acetate ion and the cyanide ion. So remember what we have to do for the acetate ion, C2H3O2 minus plus water yields acetic acid plus hydroxyl, right? I think we did this one during part 1. We did something like this because I also compared this one yields C2H3O2 minus plus H3O. So this one will have a Kb associated with it. This one will have a Ka because it's producing protons. And then when we combine those two, we get water dissociating into hydroxyl and hydronium. Okay? So when we add these two together, they're going to be equal to plus Kb. No, times, excuse me. This is an equilibrium expression. So these have to be multiplied. Equals 1 times 10 to the minus 14, or Kw. Okay? So if these two, this one times that one equals that one, then if we know what this one is for that reaction, we can find out what this one is for that reaction simply by saying Kb equals 10 to the minus 14 divided by Ka. Right? So Kb for acetic acid is just 1.8 times 10 to the minus 5 divided into 10 to the minus 14. Right? I'm going to do this and then see if I did it right. 14, oops, back up. 14, okay, and then 1.8, 5, 5. So this tells me that I've got 5.56 times 10, or 5.6. We've only got two significant figures there. Let's be kosher. 10 to the minus 10. So that should be the KB for this reaction. Okay? If we do the same thing for cyanide, just substitute this Ka value in right here, then you get 1.6 times 10 to the minus 5th for Cn. Right, so if we write the expression for cyanide plus water, where cyanide's acting as a proton acceptor, or the base, then hydrogen cyanide on this side plus OH here. That has its Kb, and the Kb then is, let's see, this one is 5.6 times 10 to the minus 10, and this one is 1.6 times 10 to the minus 5. So that means that cyanide ion is a stronger base than acetate ion. Okay. This little exercise is going to take a considerable amount of time and not necessarily give you much understanding. I'm going to try the first approach to ordering these 1 molar solutions from lowest to highest pH. So the most acidic to the most basic. We take a qualitative approach first. We're going to use electronegativities and the acid-base strengths of ions to try to qualitatively arrange them. First question. You're probably reading this while I'm erasing the board. That's a good. And when I talk fast, you'll get lost. Are there any compounds in here composed of ions from strong acid, strong base interactions? Strong acid, strong base. There's one right there. Okay? That will be neutral. It will be right in the middle of the pack. Okay? So we know where our center point is. Sodium chloride is neutral, right in the middle. Okay? So if we're going in order from lowest pH to highest, we're going to have low pH on this side. Let's just say acidic. And on this side, we have basic. But we're going to try to put them in order. Okay, what's the second? Are there any strong or moderately strong bases? Right? We have a very strong base right here. Okay? So that means sodium hydroxide is going to be the most basic. And ammonia is not a strong base, but it's stronger than, it's reasonably strong. Let's just put it that way. So we're going to put ammonia here as our proton acceptor. Okay? Are there any compounds composed of ions from weak acids, strong bases, which will make them basic? Okay, weak acid, strong base. Weak acid. There's a weak acid, but we need weak acid, strong base. Here we go. Nope, that's a strong acid. Weak acid. This cyanide ion comes from HCN, which is a weak acid and a strong base. Right? So Sodium cyanide will produce an alkaline solution with pH lower than ammonia and this one. All right, so we'll have sodium cyanide, a little more acidic than those. Okay. Are there any acids derived from halogens? Well, yes. There's HBr, there's HF. Those are the only two derived from halogens. Turns out that HBr is a much stronger acid than HF. HF is a weak acid, right? And that's because fluoride ions have the same charge as bromide ions, but fluoride ion is very, very small. So the charge density is very high, and it attracts hydrogens much more strongly than bromine does. So that means the HF will be less likely to release a hydrogen ion than HBr. So that means HF is going to be over here somewhere, and HBr will be more acidic. Now I might have to move those at some point, but that's the relative order at this point. Okay. Now, next question. Now, what do we have left? We have HCN and we have ammonium chloride. HCN is a weak acid. It should have a higher pH than HBr or HF. So that means I need to stick HCN in here. I got to move these over some. HF and HR. And then what does that mean for ammonium chloride? Well, ammonium chloride cannot be more acidic than HCN because it's a salt. It's a combination of two, a conjugate acid and a conjugate base. So ammonium chloride should be in here, right? So now we have to move them over even more. Ammonium chloride, HCN, HF, and HBr. So there's our tentative order. Most acidic to most basic. Let's see. There, 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 there. Okay, that's the qualitative approach. Now, how about the quantitative approach? Examine the Kas and the Kbs for each of these associations. We find that HBr is a strong acid. Its Ka would be meaningless. It would be so large as to be useless. HBr is a strong acid. It dissociates completely, kind of like its neighbor, HCl. Then the Ka for HF is 10 to the minus 4. The Ka for HCN is 10 to the minus 10th, so it's a weaker acid. And then the Ka for, I'm assuming for this one, this part of the molecule, ammonium, is 5.6 times 10 to the minus 10. So it's just barely weaker, smaller number than this one, just by a hair. Right? So these two are very close together. And then, of course, our neutral is no problem. Strong acid, strong base. Now, how about the Kb for the cyanide ion? 10 to the minus 5th. The Kb for ammonia, 1.8. So it's more basic. And then sodium hydroxide is a strong base, so it's all the way over to the right, and we don't even need the Kb. So that's the quantitative approach. that supports our qualitative assessment. Okay. What's next? Let me see how much more we got to go. Might not make it to chapter 15 today. Let's save that for another day. Hopefully very soon, if all goes well. All right. We're going to finish this chapter, even if I stay here to midnight. Chapter 15 is primarily on buffers, so that one shouldn't take very long. Consider the 0.3 molar solution of sodium fluoride. So we got a salt here, and we're going to put that salt in solution such that the initial concentration of sodium fluoride, when it goes into solution, is 0.3 molar. We also know that the Ka for HF is 7.2 times 10 to the minus 4. So first question, what are the major species in solution? All right. Well, if we look at what happens to HF, let's see, here we go. So when we put this in solution, I must have got those out of order. This is our first interest. Well, this, of course, describes what Ka means. Ka means HF dissociating into HNF minus. Then the major species are sodium. When you put that in solution, you're going to have sodium, you're going to have fluoride, and you're always going to have water. So then we use the major species to say what reactions are possible. First, we write down all the reactions, then we eliminate the ones that make no sense, and then we compare the ones that remain to see which one dominates. That's the train of thought. Okay. Why isn't sodium fluoride considered a major species? Because sodium fluoride is soluble. It goes right into solution. Why? Because all alkaline metal salts are soluble without fail. So sodium fluoride goes into solution. There's no NaF left over. It's only sodium, fluoride, and water. So what are the dominant reactions possible? Well, we could say that fluoride, since it's the strong base of a weak acid, then it could attack water. Since it's a major species, these are both major species, so there's going to be a lot of opportunity for reaction. F minus and water will produce HF and hydroxyl. That's a very likely possibility. What about this one? Well, of course, water and water always react. How about sodium? Is sodium going to strip a proton, strip a hydroxyl from water? Well, think about this. Sodium hydroxide is a strong base. It doesn't want to be like that. It wants to be sodium-free ions. So that reaction is not dominant, to be kind. It's actually ludicrous. So, is sodium and fluorine, will they combine and reconstitute the sodium fluoride sodium fluoride molecule? The answer is no, because this is soluble also. It's going to completely dissociate and it's not going back. So 3 and 4 are stupid. That's the technical term. So that means, based on the dominant species, that this is the controlling reaction. This is the one we have to focus on, because all the other possibilities don't matter. Well, water and water, in order to tell the difference there, we compare what's the K value for water, what's the K value for HF, right? So the KB for this one, which means a description of how far it wants to go to that side, 10 to the minus 11th, okay? Then we compare the Ka for the next one. Well, we didn't show it. But we know that the K for this value is 10 to the minus 14th. It has a weaker driving force to that side than this one does to its side, because it's 10 to the minus 11th. This one's 10 to the minus 14th. So the dominant here is this one. That is the equation, the reaction that dominates in this situation. Oh, another way to say it is the Kb for this reaction is 1,000 times larger than the Kw for that reaction. And that's true. 10 to the minus 11th is 1,000 times bigger than 10 to the minus 14th. Okay. So we did all that just to get familiar with the process of deciding which reaction we really need to focus on to determine the pH of the solution. Right? We're not going to go any farther with this one. Not yet. So now we're going to take this reaction, sodium cyanide, and go through the same process, but then we're going to carry it into our reaction ice table and go to the finish line. So Ka for HCN is this value, but we're not putting HCN in solution, right? We're putting cyanide in solution. So that means we need the Kb, because cyanide is a proton acceptor. So we need the Kb for the reaction of cyanide in water. Major species, sodium, cyanide, and water, of course, right? We throw up these reactions, and of course we eliminate the last two because they're stupid. Then we compare what's the Kb for this reaction, compare it to the K for this reaction, right? And it turns out to be 9 orders of magnitude larger. It's even bigger than the HF. Okay, now we set up our equation. Cyanide, water yields HCN and OH minus. We're starting off with 0.75 molar. That was conditioned in the original question. We have none of this and a minuscule amount of hydroxyl, right? Because we're in water, that means some of it is going to be hydroxyl, but it's so small it won't matter. So we can ignore this one and just call it 0. So we're going to ionize, we're going to lose some of this, not ionize. We're going to lose some of that as it combines with water and produce some of this, some of that in equal proportions. So our equilibrium expression then would incorporate these values. Right? We're going to say X is so small that we get this value equal. Solve for X, which would be the hydroxyl ion concentration. And you can go ahead on your own time and recalculate the K value to see if this value of X is within 5%. And I think you'll find that it is. Then we take that and find the POH. Then we convert the POH to pH and find that the solution will be 11.54 pH. Okay? So, and there are several problems in your review document of that nature where you have to decide what's the dominant reaction. Then, do you need a Ka or a Kb? If you need a Ka, that's usually given. If you need a Kb, you need to calculate it to satisfy the conditions of an anion reacting as a base with water and producing the conjugate acid and the hydroxyls. Now, next topic. Let's see. Skip that page. We've already done that page. Okay. Now, we've gone through the mechanics of these calculations. Now we're going to talk about theory. Anytime you see the word model, we're talking about a theory. That is, we're trying to explain why things happen the way they do. Okay? For binary compounds, that is, they could be bona fide acids or bases, or they could be salts. And I think our focus here is on salts. Two factors control acidity in binary compounds. One is, what's the polarity of the bond? Right? If you have a very polar bond, particularly, let's take acid as an example. Hydrochloric acid. The electronegativity of chlorine is extremely high. It's just a little bit less than fluoride. I know you couldn't see me pointing. I was pointing at the relationship of fluorine and chlorine. Fluorine, of course, is the most electronegative. Chlorine is more electronegative, less electronegative, pardon me. So what that does is it makes that bond very polar. So what does that do? Well, it shifts the electron density over here, right? So if the conditions are right, it's very easy for that proton to leave this molecule in solution, right? It becomes hydrated, takes that proton and adds it to water. So the more polar the bond, the easier it is to remove that proton. That's one factor. The next factor is bond strength, right? They're related, but they're not exactly the same. Bond strength is how much energy does it take to break that bond? Well, if it's a very polar bond, it takes just a little bit of energy. So for acidity, for the purpose of acidity, a weak bond between the proton and its molecule is better than a strong bond. For instance, acetic acid. The structure of acetic acid is like this. Okay? There's your C2. There's your H3. There's your O2. And there's the H out in front, like this. This is the proton that has the weak bond, and the polarity of the bond is fairly high, right? This way. So polarity in a weak bond means that this is the proton that is donated to water. Contrast that to these protons. These are only slightly polar, almost nonpolar, covalent bonds. They are very strong. These protons do not dissociate. So that's why we write the molecule like this, signifying that one as the acidic proton. These guys are buried in the structure and do not give up. Okay, so if we look at bond strength here between hydrogen and the halogens, okay, fluorine top, this is in the same order as on the periodic table. Fluorine, chlorine, bromine, iodine. Notice that the strength of the bond is very high up here with HF, and it decreases as we go down, right? So the amount of energy it takes to break the bond decreases, and at this point, it's so low that the acid itself is classified as strong, right? But this bond is too strong to break easily, and that's why HF is a weak acid. Okay? So there is another group of acids known as the oxyacids. And as the name implies, they're acids that have oxygen in their structure. Acetic acid would be classified as an oxyacid. but it's a weak acid. It's a carboxylic acid, for those of you who are headed for organic, and hopefully onto biochemistry. Carboxylic acids play a central role in many organic reactions and certainly in biochemical reactions. But they're weak acids. Many of the oxyacids are strong, and I would classify nitric acid as an oxyacid, sulfuric acid as an oxyacid. It's strong for the first proton. Remember the relationship. The first proton is the strong and the second one is the weak one. So the first proton is strong for this reaction. Another oxyacid, PO4, phosphoric acid. The halogen family acids, right? ClO3, the chloric acid, ClO4, the hypochloric acid, not hypo, the perchloric acid. This is perchloric. This is chloric. This is chlorus. And this is hypochlorous acids. This is what's known as an oxyacid family. Now, what does this have to do with, and let's focus on this group here, simply because we're changing one oxygen at a time, right? Everything else is the same. So what effect does that have on the acidity, the strength of the acids in this group? Well, the rule of thumb is the more oxygens you have, the stronger the acid. Okay? They're generic here, OX. This X could be almost anything, but it signifies that with this oxygen, and this hydrogen is associated with the oxygens. It's on this side, but in the structure of the molecule, it's associated with the oxygens. And the stronger the X, in this case, the X is chlorine. So for this group, the chlorine is the same. It's the same number in there. And it has the same electronegativity. So if we hold this one constant, the X, and change the number of oxygens, we find that the more oxygens you have, the stronger the acid. So the strength of the acid increases that direction as you add more oxygens. What does that mean? Well, oxygen is it's a fairly electronegative atom. So what is it doing? It's drawing electrical charge away from the proton. And with the assistance of the chlorine, because it's electronegative too. So the more of these that you get, the stronger the pull, the more polar, and the weaker the bond between the hydrogen and its associated oxygen. So that makes it easier to remove the proton. So as we go up with more oxygens, we get a stronger acid. In fact, perchloric acid is extremely strong, a dangerous acid. Now, what do we do with, if we change the X? Well, the more electronegative the X is in association with oxygens, the stronger the acid, right? So let's see if we can draw some conclusions here. We've got the same number of oxygens here between sulfuric and phosphoric, but what's the comparison of sulfur and phosphorus? Well, sulfur should be more electronegative than phosphorus because it's to the right of phosphorus. The difference might not be a lot, but we should be able to measure it in terms of the acidity of the compound. And as it turns out, this one is more acidic than phosphorus relative to the first hydrogen dissociation. That's based on the electronegativity of the X, or the non-oxygen part of the molecule. These are examples straight out of your textbook showing the K values for these various acids. Of course, perchloric acid is so strong, the K value doesn't have any meaning. Then the chloric acid is relatively strong. It has about a K value of 1. But the chlorous acid is weak, and the hypochlorous acid is even weaker. Okay? So what if we take this one and compare it to this one? Which one should be stronger? The one with more oxygens. This one is stronger than the sulfurous acid. And similarly, for nitric acid versus nitrous acid, the nitrous acid is weaker than the nitric because it has fewer oxygens. Okay. So here's a comparison of the halogens, right, with just 1 oxygen each, and all we change is the X value, right? And the electronegativity is such that chlorine is more electronegative than bromine, which is more than iodine. Now don't get this confused with the simple halogen acids like bromic acid, hydrochloric acid, hydrobromic, hydrochloric, hydroiodic acids. When we introduce oxygen, the game changes. Now, instead of the hydroiodic being the most acidic, the hypoiodous acid is the least acidic. And the hypochlorous acid is more acidic because the electronegativity of chlorine is greater than bromine, which is greater than iodine. And this one's just thrown in for, this is methanol. CH3OH is methanol. And this, if we count this as the X, its electronegativity is even less than, well, we're actually looking at the carbon, not at the hydrogen, but the carbon. And it turns out that it's even weaker as an acid. Nobody thinks of methanol as an acid, but it will dissociate a small amount of hydrogen in solution. Now, why didn't we include HOF in that series, right? We didn't put the fluorine in there. Well, it's very simple. Any temperature above 0 degrees centigrade in water, the HOF dissociates and forms HF plus hydrogen peroxide. So that reaction is moot in this current scenario. Okay, we're coming down to the line, to the finish line on this chapter. And I believe this is the last topic. Let's see. Oxides, I think. Yes. So if we have what we call acidic oxides or acid anhydrides. What does that mean? Well, if you take H2SO3, sulfurous acid, and you extract water from it, 2 hydrogens, 1 oxygen, then you get SO2, right? But this reaction can go in reverse. So it could produce this. So for the SO2, if we put that in solution, it's going to react with water and produce sulfurous acid, right? So that's why these are called acid oxides or acid anhydrides. An is the prefix for to remove or absent So the hydride is absent. This is the hydride, and it's absent from this molecule to produce that compound. So if we dissolve sulfur dioxide in water, then it reconstitutes this acid, and that's why, as an example, SO2 dissolved in water forms an acidic solution. And you can do the same thing with these and these. CO2 is a good one to go for. So what would it produce? All right, combine them together, H2CO3, carbonic acid. That's the stuff that's in your pop. And since they're in equilibrium with one another, this is in solution, and this is the gas pressure that's above the liquid in your pop bottle. When you crack the lid, it goes pop because of this producing that. Basic oxides or basic anhydrides, how do they react? Well, let's take KOH. Not KOH, CaO, calcium oxide. So what does it do in solution? Well, it takes one hydrogen from here and leaves us with hydroxyl. But of course, we need to balance that equation, right? It's only fair. So if we're going to have, we need two of these. So that gives us two oxygens. We need four. No, excuse me. We already got one over here. Let's see if I'm doing this right. Okay, no, we don't need that. That's superfluous. So we have one calcium, we have two hydrogens, and two oxygens. So that means we have two oxygens, that's it, balanced. Okay, so one calcium oxide, one water in solution gives you calcium hydroxide. That's a basic solution. Now, just an introduction to the concept of Lewis acid and Lewis base. This will be valuable for anybody in the class who's headed for organic chemistry, because so many of the reactions in organic chemistry are non-aqueous. So when we think of acids and bases in organic chemistry, chances are that we're talking about non-aqueous environments. So the concept of acid and base had to be modified by Lewis, GN, I think were his initials, GN Lewis. And what he said was a Lewis acid is an electron pair acceptor. So let's see if we can relate that to Bronsted-Lowry. So if we have let's see, what if we take, let's just take a Lewis acid, a Lowry-Bronsted acid as a proton. No, that's not good. Let's try something else. How about HCN plus water yields hydronium plus CN minus. Okay. Bronsted-Lowry says this is the acid, this is the base, this is the conjugate acid of that base, and this is the conjugate base of this acid. Okay? In this reaction, what is happening to take this one from here to here? Well, this molecule, in order to release the hydrogen, has to extract electrons from it. Right? So the electrons have to transfer from there to there. And when it does, that makes this an acid in Lewis terms because it is electron acceptor. Right? Whereas when the proton then, or the water is donating electrons so that it can accept the proton. It's attracting the proton. So the Lewis base is the electron pair donor. So it donates electrons to form that bond with this hydrogen. That's not a good example. Let's try the one they've given us. I think that'll work better. Okay. Oh yeah, this is much better. So we've got aluminum in solution. And it's interacting with water. In fact, it's interacting with 6 waters to produce aluminum and those 6 waters. Still with the charge. Okay, so the Lewis acid has to be an electron acceptor. Okay, so the electrons are donated to this aluminum in such a fashion that it forms bonds with the water. Right? So this is the Lewis acid, which is the electron acceptor. And this is the Lewis base, which is the electron, actually the pair donor. So the base donates electrons and the acid accepts electrons. So here's a comparison of each of the ones. For Arrhenius, proton producer, Bronsted-Lowry, proton donor, Lewis electron pair acceptor. So in order to be a Lewis acid, it has to be able to accept electron pairs, and vice versa. Okay, that's just a summary, and we're done for part 2, and that took forever. No wonder we didn't finish in class. So we're going to stop this video and post it.